So, imagine a safety valve mounted on top of a massive high-pressure industrial steam boiler. The pressure inside that tank is violently trying to escape, right? And if it spikes beyond a certain limit, you are looking at a catastrophic
Oh,
explosion.
absolutely. It's a terrifying amount of force.
Right. So you need an incredible amount of downward force to just hold that steam back.
Mm-hmm.
But if you actually look closely at the valve, you won't see a massive multi-ton block of iron holding it shut. You see this relatively small weight at the end of a simple metal bar.
Yeah, it really is a brilliant illusion.
It is. And today we are taking a deep dive into how you can practically cheat physics to multiply force using one of the most foundational elements of machine design.
Because when you press down on a lever, whether it's a hand pump or a workshop vise or that boiler valve, and your 10 pounds of effort suddenly transforms into hundreds of pounds of clamping force, it feels like you're getting something for nothing.
It feels like magic.
Exactly, magic. But you are just exploiting fundamental mechanical geometry. If you are joining us today, maybe you're a mechanical engineering student prepping for your machine design finals, or maybe you are studying for the GATE exam, or perhaps you're a practicing design engineer out in the field. This specific mechanism is the bedrock of everything we build.
And we're going to unpack the science, the math, and most importantly, the physical reality behind the lever. I mean, between the two of us, we have spent, over 30 years each designing products, analyzing failures, and teaching these concepts.
Yeah, a lot of years, a lot of failed prototypes we've had to investigate.
Too many to count. So treat this deep dive as a session right here in our design office with us. Let's start at the absolute beginning. Archimedes famously claims that if you gave him a place to stand and a long enough lever, he could move the entire world. Which, sounds great in a Greek text, but how do we define this for an actual engineering spec sheet?
Well, we define it by its constraints. A lever is essentially just a rigid bar pivoted about a fixed point, which we call the fulcrum. Its primary engineering purpose is to either multiply force, transfer force from one point to another, or just change the direction of that force entirely.
Right. And to understand how it actually multiplies that force, we have to establish the basic anatomy of the thing. We are dealing with four main components here. First, there is the force produced by the lever, which is the heavy lifting. We usually call this F, or the load.
Right.
Second, there is the input, the effort you have to physically apply to the system, which we call P.
The secret sauce, however, lies in the next two components, which are the distances. You have the effort arm, designated as L1, and the load arm, designated as L2. And here is a critical detail where I see students lose marks on exams and really just make errors in initial design sketches all the time.
I know exactly what you're going to say.
Yeah. The arm is not just taking a tape measure and finding the physical length of the piece of metal. The arm is strictly defined as the perpendicular distance from the line of action of the force to the fulcrum.
Let me stop you there because that is a vital distinction. Why does it have to be perpendicular?
Because forces only create rotation, what we call torque, or a moment when they act at a right angle to the pivot. If you push on a lever at a weird slanted angle, a huge portion of your effort is just uselessly compressing the metal bar directly into the hinge.
Which does zero rotational work.
Exactly. It does zero work. The perpendicular distance isolates the exact geometric leverage you're actually getting.
So if we imagine taking the moment of these forces about the fulcrum, the system has to balance perfectly, like a seesaw.
Yep, a seesaw.
The load multiplied by the load arm has to equal the effort multiplied by the effort arm, or, mathematically speaking. F times L2 equals P times L1.
And when we look at that simple balance equation, F times L2 equals P times L1, we uncover two essential ratios. If we divide the load by the effort, F over P, we get the mechanical advantage, as in how much force am I getting out compared to what I actually put in.
Right.
Then, if we divide the effort arm by the load arm, L1 over L2, we get the leverage. In a perfect system, your mechanical advantage perfectly equals your leverage.
Which means, practically speaking, if I want to lift a 1-ton engine block with just my own body weight, I just need to make the effort arm L1 incredibly long and the load arm L2 incredibly short.
You could, well, on paper anyway.
Yeah.
Out in the real world, space is your ultimate constraint.
Very true.
I mean, you cannot fit a 12-foot lever inside a compact automotive transmission casing or a precision medical device. When you require high mechanical advantage but only have a few inches of clearance, you can't just extend L1 indefinitely.
So what do we do?
Instead, we use compound levers. We link multiple smaller levers together in a series, so the output force of the first lever literally becomes the input effort for the second lever. This multiplies the mechanical advantage sequentially without taking up, all that linear space.
That makes perfect sense for fitting massive power into a tight package. Now, depending on how we arrange these 3 points, the effort, the load, and the fulcrum, we classify levers into 3 distinct types. Let's explore the physical implications of each, starting with a type 1 lever. In a type 1, the fulcrum sits squarely between the load and the effort.
With a Type 1 arrangement, the mechanical advantage is totally variable. Since the pivot point is somewhere in the middle, your effort arm could be shorter, it could be equal to, or it could be much longer than your load arm.
But we generally want it to be longer, right?
Right, we generally design the effort arm to be the longer one, to actually gain that force multiplication. You encounter Type 1 levers constantly out there. Rocker arms pushing down on overhead valves in an internal combustion engine, the bell crank levers operating heavy railway signal mechanisms, or just a standard water hand pump.
Okay, moving on to the type 2 lever. This is where the load F is trapped in the middle between the fulcrum on one end and your effort on the other end. A classic real-world example of this is a wheelbarrow.
Oh, that's a perfect example.
Yeah, the wheel is the pivot, the dirt is the load in the middle, and your hands provide the effort at the handles. In heavy industry, this is the exact setup for those lever-loaded safety valves on boilers we talked about earlier.
And notice the geometric forced hand here. Because the load is in the middle and the effort is on the far outside edge, the effort arm is always, by definition, longer than the load arm. So your mechanical advantage will always be greater than 1.
Always.
Always. Type 2 levers are incredibly efficient, guaranteed force multipliers.
Which brings us to the type 3 lever. And honestly, this setup feels completely counterintuitive.
It really does.
In a type 3, the effort is placed in the middle, between the fulcrum and the load. That means your load arm is now the long one, and your effort arm is the short one, which means your mechanical advantage is strictly less than 1. Wait, so I'm putting in more force than I am getting out. I am actively losing force. Why on earth would any engineer ever design a system like this?
I know, it sounds like a terrible design flaw until you consider the trade-off. You are sacrificing force to gain speed and distance.
Oh, right.
Yeah, a small, powerful movement at the center of the lever translates to a very fast, sweeping movement at the tip. In heavy machine design, you generally avoid Type 3 levers because losing force is a massive disadvantage. But think about simple things like tweezers or a picking fork or even the human jaw.
A human jaw, wow.
Yeah, when your goal is precision control, rapid reach, or sweeping a large area quickly rather than crushing power, the Type 3 lever is exactly what you need.
Okay, that clarifies the taxonomy perfectly. Now we really need to transition from understanding what a lever is to actually building one from scratch. Let's say you are a junior design engineer, right? You have a blank CAD screen and you need to design a lever for a new machine. You don't just start by picking a material or drawing a pretty shape. Step 1 is always mapping the invisible forces.
Absolutely. Force analysis dictates everything that follows. Usually, the load, the required force F, is handed to you in the design brief. Say, your mechanism needs to apply 500 newtons of force to actuate a clutch. Your first task is to calculate the effort P required to achieve that, using our balance equation. F times L2 equals P times L1.
Right, so we figure out the effort, P, and we have the load, F, but that lever is resting on a pivot pin. All of those downward or upward forces are converging on that single central pin. We call the force acting on the pivot the reaction force, or R. If we don't calculate R accurately, that pin shears in half and the entire machine fails.
And that's why we rely on free body diagrams to isolate that reaction force. Let's look at a Type 1 lever. You have the load pushing down on one end and your effort pushing down on the other end to lift the load.
So they're both going down.
Right. Both forces are acting in the same downward direction. To keep the whole bar from just falling through the floor, the fulcrum pin in the middle has to push up with enough force to support both of them. Through basic vertical equilibrium, the reaction force R simply equals F plus P.
The pin just takes the full brunt of both. But in a Type 2 lever, the arrangement changes the math completely.
Indeed it does. With a Type 2 lever, the fulcrum is at one end pushing up, the effort is at the other end pulling up, and the heavy load is in the middle pushing down. Setting up the vertical equilibrium, the downward load F has to be balanced by the upward reaction R plus the upward effort P. So F equals R plus P.
And if we just isolate the reaction force, R equals F minus P.
Exactly.
So the pivot on a Type 2 lever actually experiences less raw force than a Type 1, assuming all the forces are perfectly parallel. But, as we know, in complex machinery, forces rarely line up perfectly parallel. They pull at odd angles.
Yeah, and when forces S and P are inclined to one another, we can't just do simple addition or subtraction anymore. We have to use the parallelogram law of forces. The magnitude of the reaction R becomes the vector resultant of F and P. Furthermore, the geometry dictates that the line of action of this reaction force R must pass directly through the intersection point of P and F and straight through the center of the fulcrum.
Let's ground this with a specific, highly common mechanism, the bell crank lever. It's an L-shaped lever used constantly to change the direction of motion, say, taking a horizontal pull from a cable and turning it into a vertical push on a valve. The arms are inclined at an angle to one another, let's call it angle theta. Since the forces are at an angle, finding the reaction R at the fulcrum involves the law of cosines. Mathematically, R equals the square root of F squared plus P squared minus 2FP times the cosine of theta.
I know that equation gives some students anxiety just hearing it out loud,
Yeah.
but let's look at the physical reality of what that math is actually doing. Because the forces are pulling at an angle, they're somewhat fighting each other, creating a complex stress point. But, engineers love simplicity.
We really do.
So there is a massive design shortcut here. We often deliberately design bell crank levers so that the two arms are at a perfect 90-degree right angle to each other.
Oh, I know exactly where this is going. When the theta is 90 degrees, the cosine of 90 is 0.
Yes. That entire messy, complex chunk of the equation, the minus 2fp cosine theta, it just vanishes into 0. The math beautifully collapses into r equals the square root of f squared plus p squared. It's just the Pythagorean theorem.
A right triangle.
Exactly.
Yeah.
By designing the arms at 90 degrees, the forces no longer interact in that messy, angled way. It makes the lever incredibly robust, it's easy to manufacture, and mathematically, it is clean to analyze.
Brilliant. So we've mapped our forces. We have F, P, and R. We know the massive forces this lever can generate. But force is a double-edged sword. The same pressure that actuates the heavy clutch is actively trying to snap our metal lever in half. Which brings us to step 2, shaping the lever arm to survive bending stress. And I want to use an analogy here. Picture the lever arm like a diving board over a pool.
Oh, bending mechanics act exactly like a diving board.
Right. When a heavy diver stands on the very end of the board doesn't snap right under their feet. The bending moment at the very tip is 0. The board bends and is most likely to break all the way back where it is bolted to the concrete. For a lever, that anchor point is the central hub around the fulcrum pin. We call this reinforced hub the boss.
And if you chart a bending moment diagram for a lever, it starts at 0 where the effort is applied and increases linearly until it maxes out right at that boss. But we need precise dimensions here. The lever arm doesn't start bending from the dead center of the pin. It effectively starts bending at the outer edge of that reinforced hub.
Because the boss is basically a thickened, solid ring of metal. If your fulcrum pin has a diameter of D1, industry standard practice is to make the outside diameter of the boss twice as thick, so 2D1. This means the radial distance from the exact center of the pin to the edge of the boss is simply D1.
Knowing that, we can calculate the maximum bending moment, MBE. It is the effort P multiplied by the distance. But the distance isn't the full length L1. It is L1 minus D1.
Oh, because you subtract the radius of the boss.
Right, because that thick hub isn't bending at all. The stress is entirely concentrated on the arm extending out from the edge of the hub.
So once we have that massive bending moment, we have to design the cross-section of the arm to fight it. You can make the arm rectangular, you can make it elliptical, or even an I-section for massive industrial machinery. But let's focus on rectangular cross-sections, as they are incredibly common. You don't just pick random dimensions. You have a width B and a depth B. The golden rule in lever design is that the depth D is usually taken as twice the width B.
And we really need to talk about why that rule exists. It comes down to a property called the moment of inertia. But before we drop an equation on you, we need to understand the neutral axis. When you bend a metal bar, the material on the top curve is being violently stretched apart in tension. The material on the bottom curve is being crushed together in compression.
But what about the material right in the dead center?
It's doing almost nothing. That imaginary line running through the center where the material is neither stretching nor compressing is the neutral axis. It is lazy material. To resist bending, you want to put as much of your metal as possible far away from that neutral axis out to the top and bottom edges where the extreme stretching and compressing forces are actually happening.
Think of the wooden floor joists holding up the room you are sitting in right now. The carpenters don't lay those 2x10 wooden boards flat on their wide side. They stand them up vertically on their narrow edge. You need that deep vertical depth to fight the bending load of the floor.
And the math proves the floor joist analogy perfectly. For a rectangular section, the moment of inertia, denoted as I, equals the width b times the depth cubed, all divided by 12. Notice that the depth d is cubed.
Wait, break that down for me. If I double the width of my lever, I double its strength. But if I double the depth because of that cube function, I get 2 times 2 times 2. I get 8 times the resistance to bending.
You get an exponential boost in strength without adding massive amounts of weight or material. That is exactly why depth is your best friend in structural design. And the exact same logic applies to an elliptical cross-section, where the major axis is oriented in the direction of the bending force and is cubed in the inertia equation.
So you take your maximum bending moment, you choose your deep cross-section to get a high moment of inertia, and you use the bending stress equation to ensure you aren't exceeding the safe limits of your cast iron or forged steel. That secures the arm. But that brings up a new problem. We have a perfectly balanced, incredibly strong lever arm, but it's totally static until we design the pivot mechanism. That is step 3, designing the fulcrum pin.
The fulcrum pin takes the full brunt of the reaction force R that we calculated back in step 1. The two crucial dimensions we need to solve for are the pin's diameter, D1, and the length of the pin sitting inside the boss, L1.
Now, your intuition might say, we designed this pin against shear stress. Like, we don't want the pin to just get chopped in half like a carrot under the weight of our... And we do check for shear eventually, but the primary dimensions are dictated by something called bearing consideration.
Bearing consideration is required because a lever is a mechanism of motion. It is rotating around that pin. Whenever you have two heavy metal surfaces rubbing against each other under a heavy load, your primary enemy is bearing pressure.
The projected area taking this load is a rectangle formed by the pin's diameter times its length, so D1 times L1. The bearing pressure, which we call lowercase p, is simply the reaction force R divided by that projected area.
To optimize this, standard industry proportions suggest the ratio of the pin's length to its diameter should be between 1 and 2. Furthermore, we never just stick a steel pin directly into a steel lever boss.
Oh no, never.
The friction would destroy both parts in no time.
Wow.
We introduce a sacrificial layer, a bushing, typically made of phosphor bronze about 3 millimeters thick, fitted perfectly inside the boss.
Because phosphor bronze is softer, it has excellent anti-friction properties, and if it wears out, you just tap out the cheap bushing and replace it, rather than throwing away an expensive forged lever. We also pump lubricant in there, but the permissible bearing pressure for that bronze bushing is shockingly low, usually between 5 and 10 newtons per square millimeter.
Very low.
I mean, I'm looking at this, and mathematically, bearing pressure is just force divided by area, but later in the textbook, the safe limit for crushing stress, which uses the exact same formula of force divided by area, is way up at 150 newtons per square millimeter. Why on earth is one limit 10 and the other is 150? Am I missing a massive variable here?
You aren't missing a mathematical variable. You are missing a physical reality. And honestly, this is a massive trap that catches young engineers all the time. Confusing bearing pressure with crushing stress will cause catastrophic failures in the field. The absolute crucial difference between the two comes down to one thing: relative motion.
So whether the parts are actually moving against each other or just sitting perfectly still.
Precisely. Bearing pressure is the design criterion when they're at IS relative motion. A fulcrum pin oscillating in a lever, a power screw turning inside a nut, a shaft spinning in a bearing. Because they are moving under heavy load, you are relying entirely on a microscopic film of oil or grease to keep the metal surfaces separated.
Right, the oil is doing the work.
Yeah. If the pressure exceeds that tiny 10 Newton per square millimeter limit, the load physically squeezes all the oil out of the joint. The microscopic peaks and valleys of the steel and bronze make direct, dry contact. They literally weld together through friction, galling occurs, and the moving joint just tears itself apart.
Ah, so a bearing failure isn't the metal physically crushing into dust. It's the joint failing to act as a moving part. It seizes up.
Yes, it seizes. Crushing stress, on the other hand, is the design limit when there is NO relative motion. Think of a cotter pin locked tightly into a joint, or the threads of a bolt tightened down hard. They are static. Because they aren't sliding, we don't care about preserving a delicate oil film or friction wear. The solid metal can absorb massive amounts of static force before the atomic structure of the steel literally crushes.
Wow.
That is exactly why static crushing stress limits can safely hit 150. If you accidentally use that high crushing limit to size a moving fulcrum pin, the pin will be way too small, the pressure would be too high, the oil will squeeze out, and your lever will seize on day one.
That distinction, the oil film versus the solid metal, is the exact kind of physical engineering insight that takes equations off the chalkboard and puts them into the real world. Let's synthesize everything we've discussed and recap the complete design lifecycle for our listeners.
Designing a robust lever is a strict three-step causal chain. Step 1. Force analysis. You use the balance of moments to find your required effort, P. Then you use vertical equilibrium, or the parallelogram law, for angled bell cranks to find the reaction force, R, threatening the pivot.
Step 2. Design the lever arm. You treat the arm like a diving board to find the maximum bending moment right at the outer edge of the reinforced boss. Then, you design a cross-section, usually rectangular or elliptical, utilizing depth to exponentially increase your moment of inertia, keeping your material far away from that lazy neutral axis.
Finally, step 3. Design the fulcrum pin. Because the joint must move smoothly under load, you size the pin strictly based on low-bearing pressure to protect the lubrication film, completely avoiding the trap of high-crushing stress limits. You implement a sacrificial phosphor bronze bushing and respect the standard length-to-diameter ratios.
Whether you are designing the rocker arms in a high-performance racing engine, the intricate linkages of a massive manufacturing press, or literally reverse engineering the simple paper puncher sitting on your desk, this workflow is your roadmap.
These principles are remarkably universal. In fact, to leave everyone with a final thought, I want you to consider the extreme frontiers of what we discussed today. We spent a lot of time talking about massive macro-scale applications, steam boilers, wheelbarrows, automotive clutches. But what happens when Archimedes' leverage is shrunk down to the atomic scale?
The exact same physics applies, just incredibly small.
I highly encourage our listeners to explore the field of MEMS microelectromechanical systems. Right now, inside the accelerometer of the smartphone sitting in your pocket, there are microscopic levers etched entirely out of silicon.
That is wild.
The exact same equations for perpendicular moment arms, the exact same concepts of depth and bending stress to the boss, are being used by engineers today to design levers smaller than a human hair for cutting-edge medical devices and aerospace sensors.
It is incredible proof that the fundamental geometries Archimedes pondered centuries ago are not just historical artifacts. They are completely future-proof engineering tools. Thank you for joining us in the design office today for this deep dive. Keep asking those foundational questions, keep sketching out those free body diagrams, and we will catch you on the next one.